So who am I? My name is Evan Chang. You can call me Squareman. You can call me Square. I don't care. I basically introduced myself last week, but anyways, I'm from New Jersey. I'm from High Technology High School. I'm a freshman, and I graduated in 2024. So what did we do last week? So last week we talked about basic manipulations, right? So that was extending the basic closed forms that we learned in week 1. So these included pairing up terms in our sum. They included grouping up terms in our sum. They also included simplifying our summand directly in order to basically state it in a different way. We also did some infinite sums, and we also talked about multiplying sums together. So that's factoring sums factoring a large sum into 2 smaller sums. So what are we going to do this week? So this week we're going to talk about one of the most important manipulations that we basically left off last week because it would be too long essentially, and this deserves its own week, and that is splitting the summand. So splitting the summand is a pretty broad idea that we'll get into later. We'll be talking about telescoping sums, and you've probably heard this term before. It's a very well used summation technique. It's found all over the place. We'll be talking about we'll talk about a little bit about partial fraction decomposition, which is a technique that is generally used to simplify telescoping sums. And we'll talk a little bit about basically splitting into multiple pieces, because most of the time you're splitting it into 2 parts, but sometimes you'll have to split it into like 3 or 4 or 5 parts, depending on how bashy the question is. So here's an introduction to what we're doing today. So what is the goal, right? So when we're doing a splitting the summand problem, we're usually given a summand that's pretty weird. It's pretty complicated. It looks very hard to simplify. And the key is to rewrite the summand. So I guess you could call it a variation of simplifying the summand directly. So you're basically writing the summand as the sum of smaller summands added together. When I say added, I still mean that the summands, they can be negative. And as you'll see, oftentimes you do want at least one of them to be negative. So there's 2 ideas. And so there's 2 things that you can do with this strategy. So the first thing is that you can make one complicated sum essentially become 2 less complicated sums, right? So you say you have like one summand, you can split the sum into 2 sums for the 2 components of that summand. And this will make sense later. The other idea is for the summands to essentially cancel out. And this is what is called a telescoping sum. And usually you're going to be left with 2 or 3 terms left over at the end. And then you'll just have to compute those few terms by hand. And so a word of warning, do not forget about the summands that cancel. So this so a lot of people, they might forget like the tiny term at the end that cancels when you split the summand into two parts, and then they'll just make us silly, and then the points will be gone. It's a catastrophe. It's horrible. Do not forget about any extra terms. It's the same idea as pairing up the terms together, right? You don't want to forget about any terms in the sum that you might have forgotten about. Okay. So what's the formula for splitting the summand, right? So what is like the mechanism? Yes. So it's a very simple idea. It's a very simple idea. It's actually it's just I guess the associative property, the commutative property. So let's say you have the sum, right, from k up to n of, and each summand, right, is a function of I, but this function can be expressed as a sum of two other functions, right? So what you can do is that you can split the summand, right, into its two respective components, which is, in this case, we're gonna call them f of I, and we're gonna call them g of I. So then the sum is gonna become the sum of f of I evaluated from k to n, and the sum of g of I evaluated from k to n, right? So it's a very simple idea, but it's quite a powerful one. All right, so now here's the telescoping sum formula. So most telescoping sums, not all of them, they're gonna follow a very formulaic pattern. It's gonna be very formulaic. It's gonna be a little bit boring. So first, you're gonna be summed from an integer k to an integer n, this summand right here. And the key is that there's usually going to be a function of I, which we're going to call f of I, such that each term in the summand, right, the I term in the summand can be represented as f of I minus f of I plus 1. And I did say addition earlier, so I guess you could write it like this, like f of I plus the negative of I plus 1, but it doesn't matter at all. But anyways, if you're able to write our summand like this, then something very cool can happen, right? It's that you can force a lot of cancellation. And forcing, of course, you've heard the term because forcing cancellation is it's a very common idea in summation problems, but it's just another way to do it. So you write each summand as the difference between f of I and f of I plus 1. And you can see here, right? So f of k minus f of k plus 1 plus f of k plus 1 minus f of k plus 2, blah, 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 all the way to f of n minus f of n plus 1. So you can see that all these terms, right, a lot of these terms are going to cancel out because there's going to be one negative copy from one summand, and there's going to be one positive copy that's going to come from next summand. And then you just keep canceling off these terms, and I'll leave it up to you to verify that what we're left with, we're only going, in this case, we're only going to be left with two terms, and those terms are the f of k that we started with at the beginning, and the f of n plus 1 that we're left with at the end. And that's why this technique is so powerful, right? You can essentially reduce the entire sum to finding the sum or difference of like two terms, and then you just have to evaluate these terms by hand. Yeah, so this, of course, this is like a lot of notation. I use like f of I and g of I, f of I and f of I plus 1 as like placeholders, I guess, for So that's why this notation looks a little bit scary. But I think if we illustrate with a few examples, then it'll become a little bit clearer. So before we get to like the telescoping sums, so the telescoping sums are like the main thing that we're going to be talking about, right? But sometimes you're going to be using the idea of splitting the summation to just split our sum into two parts, into two smaller sums. And these two smaller sums, they're usually going to be a little bit easier to evaluate, right? So this problem is from Amy, and it's asking for the sum of the digits of this sum over here, right? So usually let's just pick up on the pattern. The first integer is 9, second integer is 99, the third one is 999 plus blah 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 plus an integer that's 321 digits, and it's composed of entirely of nines. I'm not gonna say the full name, obviously. But anyways, so the key is to find a better way to express these terms, right? Because just with the 999s, whatever, it's a little bit weird to deal with them. You're not going to be like adding them together in like a addition thing, right? You're not going to be doing that. So you want to find a better way to express these terms, and the better way to express these terms is going to be 10. So the first one is going to be 10 to the power of 1 minus 1, right? 10 minus 1 equals 9. The second one is going to be 10 to the power of 2 minus 1. That's going to be 100 minus 1, which is 99. The third one is going to be 10 to the power of 3 minus 1. That's going to be 999. And the last one is going to be 10 to the power of 321 minus 1. And you get this thing right here. I'm not going to say the full name. But anyways, you might see now that we can write this sum, right? We can write the sum as it's always good practice to write things in summation notation. So we're summing the quantity 10 to the power of I minus 1 as I goes from 1 to 321. So the key idea now is to split the summand, right? We're going to try to split the summand into two different sums. So you might have guessed by now that the two components is one of them is going to be 10 to the power of I, and the other one is going to be not minus 1. It's going to be a constant, right? Don't forget the minus, but not forget the negative. But anyways, this becomes, so one of these terms, it's going to become like 1, 1, 1, 1, whoa, 1, blah, blah, 1, 0, right? Hold on. So this sum right here is going to be this 1, 1, 1, 1, 1, blah, 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 and then 1, 0, this thing right over here is a geometric series, but we don't really want to simplify it because we're looking at the sum of the digits, right? So we want to look at how it's going to be written in base 10. So the other thing is going to be negative. So we're going to subtract I summed, no, 1 summed from I equals 1 to 321. This is just 321. All right. So we know that the last, so now what we're gonna try to do is find the sum of the digits of this number, right? So we have this integer that's going to be written as 1, 1, 1, 1, a bunch of ones followed by a 0, and then we're going to subtract 321 from that, and then we're going to get our final answer, and what we want is the sum of the digits of this answer, right? So to do that, we're actually going to have to do something like this. We're going to have to do a little, you have to do a little subtraction, right? Oh, sorry. All right, so so let's look at what we get, okay? So the last digit is going to be 9 of our difference. It's going to be 9. The next digit is going to be 8. You can follow my arithmetic along with me. The next digit is going to be 7. And then this covers over, so this becomes a 0. And then what we're going to have is that we're going to get a bunch of 1s, right? So all these 1s from this point on, you're just going to go straight to the answer. So we basically have a bunch of 1s, a 7, an 8, and a 9. So now we want to find the sum of the digits of this number. So this is the point where it's very easy to make an off by 1 mistake, right? So an off by 1 mistake is essentially where you like write, I don't know, like 1 off the actual answer. It's a very common mistake in Amy. Amy has like a lot of off by 1 questions. So you have to make sure that your answer is not like 1 greater or like 1 less than the actual thing. I know a bunch of people who do that regularly. But anyways, first of all, how many 1s are here, right? So you might see that 3 of our 1s are going to be gone, and there were initially 321 1s in total. So we're going to have 321 minus 3. This is the sum of the bunch of 1s that we're talking about. We're going to add a 7. We're going to add an 8. We're going to add a 9. And I'll leave it to you to confirm that our answer is 342. So you can see how like someone might have did an off by 1 on this question. And considering that it was like problem 1 on the actual test, that I think it's pretty brutal. Getting your first question wrong with Amy. Definitely didn't do it this year. Anyway, okay. So our next example is also not a telescoping question, but it's from the Carnegie Mellon Informatics and Mathematics competition. I don't know. So it's well known that the mathematical constant e can be written as in the form 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, so on. So it's going to ask you to determine the value of this sum in terms of e, which is clearly it's a bit harder than our last question, right? So this is an infinite sum. So what we're going to have to do is we're going to have to express it as the sum of other infinite sums that we do know are going to converge. And we're going to assume that one of the sums is going to involve e in some sort, right? Because otherwise, why would they tell us this? So let's take a look. Let's take a look at. So the key to this problem actually is to think of it not as a sum in terms of j, but to think of it as a sum in terms of the floor of j over 2, right? So this is a little bit confusing, but you'll see what I mean when I write it in this following way, right? So we're gonna sum this quantity over all possible values of the floor of j over 2. So the floor of j over 2 can be anywhere from It's going to be from anywhere. Oops, it's supposed to be 4. I'm sorry. Anyways, it can be anywhere from 2 to infinity. So the key to this is to see that for every k, it's going to be seen 2 times in this sum. Every value of floor j over 2 is going to be seen 2 times in the sum. It's going to be seen 1 time as in the form of 2k over k plus 1, k factorial. So when j equals 2k, then this summand is going to evaluate to this summand. And the other thing is 2k plus 1 over k factorial. So if j equals 2k plus 1, then this summand is going to evaluate to this term over here. So essentially, you can think of it as like squishing our sum down by half. So actually, you might think of this as sort of like the reverse of splitting the summand, right? So we're essentially grouping every 2 terms into 1 term. So we have 2k over k factorial, k plus 1 over k factorial. We're going to group them together into 1 term. So yeah, it's a little bit of a tricky concept, but what we've done is that we've managed to get rid of this weird floor looking thing, right? So the whole goal of this was to get rid of the floor j over 2, because floors are your enemy. Your goal, whenever you see floors, ceilings, rounding to the nearest integer, like these sorts of things, your first goal should always be to get rid of them, right? You want to get rid of these horrible functions because they're absolutely horrible to deal with. So the way you deal with them is by casework on whether j can be represented as 2k, whether j is even, or whether it can be represented as 2k plus 1, which is when j is odd. Anyways, so how do we simplify from here? Once we get to this sum, we know that our sum becomes this sum. How do we simplify this? So we're actually going to do a little bit of manipulation, right? So this sum, I'll leave it to you to confirm, sum becomes 4k over k factorial plus 1 over k factorial. So the term on the left, this is going to become 4 over k minus 1. Excuse me, I'm writing all over the place. But one of these terms is going to become 4 over k plus k minus 1 factorial. And the other term is going to become 1 over k factorial. So after all this is said and done, we reduce our sum into 2 infinite sums. So one of them is going to be summing the value 4 over k minus 1 factorial over all k from 2 to infinity. And the other sum is going to be summing the quantity 1 over k factorial from k equals 2 to infinity. And from there, it's not very hard. I'll leave it to you to verify that our final answer is going to be 5e minus 3. So, and this is going to be using the fact that e is going to be equal to the sum of the reciprocals of increasing factorials, right? So I was pretty unclear on that. So let me just review for a second. So first we were given this infinite sum, which had a really ugly looking floor in it. So by summing the quantity, so by summing the summand over the quantity floor of j over 2 instead of the quantity j, we were able to magically get rid of this pesky 4 over j over 2 term, and instead we were able to simplify it into something that looked like this, which we could easily verify, right? So anyways, that is that. So this is good. So that's it for this problem. The next problem is from OMO online math open. So and also okay, so what we have here is this really weird sum, again involving factorials, and we're summing this quantity over all k from k equals 2018 to infinity, and we want the least integer greater than or equal to this sum, right? We want the ceiling of the sum. So the first thing you should do is just forget about the ceiling for a second and just try to get this sum written in a bit of a better form. All right. So how do we do this? So actually, it turns out with complicated sums like these weird sums that you don't really know how to deal with properly, the first thing you should do is to try to just list out some terms. So when k equals 2018, what does the sum evaluate to, right? So 2019 factorial plus 2018 factorial over 2018 factorial. This is going to evaluate to 2019 minus 1. All right. So, and then what if k equals 2019, right? So then you might be able to check that this, oops, I wrote this wrong here. Yeah, now that's correct. So 2019 minus 2018 factorial over 2019 factorial, this becomes 1 minus 1 over 2019, right? And then if k equals 2020, you might be able to see that we're gonna have something like 1 over 2020 minus 1 over 2020 times 2019, and so on, right? So what are we left with, right? So the key is that to focus on the integer term. So let's start with the integer term, right? So we start with the integer term 2019. And you might be able to see that since these terms cancel, after these terms, all of these terms, right, they're gonna be very small. 1 over 2019. That's a very small number, and these are even smaller. If you write another term, let me just write another term just for kicks. Oops, I am running out of room. Sorry. But anyways, as you can see, these terms get small and they get small really fast. So what do we add, I guess, to 2019 to get our final answer? So first of all, these two integers cancel out. We have minus 1 over 2019 plus 1 over 2020. this becomes 1 over, this becomes this. We have minus distraction plus distraction minus distraction plus you could then and then it's plus so on, right? So this sum, right, it keeps going on. So first of all, what you might notice is that you can essentially pair these up, right? So these two terms, when you pair them together, they're going to sum to something that's negative. These two terms, we're going to sum to something that's negative. These two terms, we assume we're going to sum to something negative. And ultimately, what you might be able to see is that all of these terms are going to become very small very fast, right? So you're essentially gonna be subtracting these very small things from 2019 is what I'm saying. So and each of these fractions, each of these pairs of terms are going to sum to a negative value, and that's because one of the denominators is greater than the other denominator, right? Anyways, I'm saying a lot of arithmetic, and you can probably verify that on your own time, but I'm just speeding through it. Anyways, if you got to this point, most people, you would probably just guess that the answer is just going to be something really, really close to 2019, just slightly less than 2019. That makes the answer 2019, and you would be correct. And if you wanted to be a little bit more rigorous, then you could actually say that these subtracted terms are going to be their absolute value. It's going to be less than the sum of an infinite geometric it's going to be less than the sum of an infinite geometric sequence, right? So something like this, and this evaluates to something that's a little bit less than negative. That's a little bit greater than -1. So anyways, the answer is going to be 2019. Okay. So this is the first telescoping problem that I'm going to cover, and it's about the triangular numbers. And you've seen this a billion times before. It's just the sum of, so the nth triangular number is the sum of the first n integers, which is just n to the n times n plus 1 over 2. So we have this over here, the sum of the integers from 1 to I. So the first thing you do when you see the sum, you're gonna have to find a closed form for the summand, right? And thankfully, we've already given the closed form to you. It's gonna be this over here, right? Because we're asking for the reciprocal of this closed form. But anyways, from here, you're gonna try so you might have seen, right? So the key insight here is that you're going to, when you subtract 2i and 2 over I, and you subtract 2 over I plus 1 from that, what you're going to get is you're going to get 2 over I times I plus 1. So that's what you're going to get. So now you can see that our function fi that we talked about earlier, right? It's going to be 2 over I in this case. But anyways, what we're going to have is that we're going to have the sum 2 over 1 minus 2 over 2, right? Plus 2 over 2 minus 2 over 3 plus 2 over 3 minus 2 over 4. All the way up to 2 over 100, right? Minus 2 over 101. So as you can see, by the power of telescoping sums, almost all of these terms are going to cancel out. All these terms are going to cancel out. So the only two terms that we are left with is going to be f of k, which is in this case f of 1, 2 over 1, and f of n plus 1, that's minus 2 over 101. So we're going to subtract 2 over 101 from this. And if you do a little arithmetic, hopefully I don't get this wrong, you should get 200 over 101. Correct me if I'm being stupid again. Anyways, on to the next example. So in this example, we're dealing with a very famous sequence called the Fibonacci sequence. So the Fibonacci sequence is just defined as the following. So f of 0, no, the zero, I don't know, the 0 term of that Fibonacci sequence is just 0. The first term is 1. And the nth term is the sum of the n minus 1 term plus the sum of the n minus 2 term, right? The sum of the two previous terms in the sequence. So you can keep listing these out. There we go. There we go, something like this. You see them everywhere. But anyways, what you do is that we have the sum over here. I added 2021 for the year. So we want to simplify the sum. And in general, if you didn't pick up on the pattern yet, so the nth term in the sum, right, is going to be f of, it's going to look something like this. And there's going to be 2022 terms in the sum clearly. But anyways, we have this term right here. So how do we make this term telescope, right? That's a little bit puzzling. So the answer to that question is you have to use the recursive formula for the Fibonacci sequence, right? So what you do is that you write f of n minus 1, you write it as f n plus 1, something like this, okay? So now our summand looks something like this. So now it's clear that we want one of our fractions to have f of n in it, and we want one of the fractions to have f of n plus 1 in it. We want to separate it into two fractions, right? So you might be able to see, it's not too hard to see that this summand actually simplifies to 1 over the nth Fibonacci number minus 1 over the n plus 1 Fibonacci number. So from there, you can see that most of our terms telescope, we're going to have 1 over 1 minus 1 over 1 plus 1 over 1. Oops, I skipped the term, didn't I? That's not. Okay. Plus 1 over 2 minus 1 over 3. 1 over this, 1 over this. Okay. So once again, by telescoping sums, the second and third terms cancel, the fourth and fifth terms cancel all the way up to this term. So what we're left with is 1/1 minus, which is 1, left with 1 minus 1 over the 2023rd Fibonacci number. That is our final answer. You might have noticed that the first term is actually 0, because so technically you can actually erase it and it wouldn't even matter. But anyways, on to the next problem. This one is a bit of this one is quite tough. But anyways, in this problem, you're given 3 sequences. You're given the first sequence is defined such that the kth term looks like this. The second term is defined such that the kth term looks like this. And the third sequence is defined such that the kth term looks like this. And okay, so your goal is to simplify the sum of the first 2,215 terms of this term over here. Okay. So right off the bat, right? If you saw this in context, you would. It looks pretty scary. It looks pretty brutal, right? So you could probably guess that the terms they're gonna telescope somehow, right? But how exactly they're gonna telescope is still a little bit unknown. So let's take a look at. So first of all, what should we be focusing on, right? So what should we be focusing on? So first of all, just the cube root thing. The cube root thing is a little bit interesting. Keep an eye on that. So what we're guessing is that this term, once we can express this term as some term cubed. So then you take the cube root of it, the radical goes away, and then you can do your telescoping in peace. So what we want is to get rid of this nasty cube root thing by representing this as the cube of something. Okay, what else? So the other thing is to notice the k plus 1, k minus 1 terms, right? K plus 1, k minus 1 terms. So the interesting thing is, so you might have seen that we might be able to do something if we let one term, set one variable, I guess call it x equals cube root of k plus 1, y equals the cube root of k minus 1, okay? So now we have something very cool, right? Now we have something a little bit interesting, a little bit spicy. So this term becomes x squared minus x squared y. This term becomes y squared x. So now things are starting to get a little bit interesting, because what happens is 2 minus 3 of pk minus qk, it's going to become 2 minus 3x squared y and plus 3y squared x. So now things are looking a little bit. It looks a little bit like it's a little bit like the expansion. Looks a little bit like the expansion of x minus y cubed, right? So the only thing that separates them is that the expansion of x minus y cubed, it has x squared plus y cubed. In this term, we actually have something weird. We have a constant of 2. So what do we do, right? Well, you might have noticed that the cube roots here are here for a reason, and y minus y cubed. So the cube roots here for a reason, and the reason is that if we cube x, get k plus 1, we cube y, get k minus 1. So actually, we get x cubed minus y cubed equals 2. So the problem has actually been magically contrived to make sure that this term right over here, this term inside the cube root, it evaluates to cube of a term. And this term actually turns out to be cube root of k plus 1 minus the cube root of k minus 1. That becomes this. Okay? So now once we take the cube root of this term, we can finally do our telescoping in peace. We actually get, magically, that r of k is going to be equal to the cube root of k plus 1 minus the cube root of k minus 1. So we're actually going to have cube root of 2 minus cube root of 0 plus cube root of 3 minus cube root of 1 plus cube root of 4 minus cube root of 2 plus cube root of 2016 minus cube root of 2014, something like this, okay? So the last trick this question has is that it doesn't really telescope in the usual way, right? So this term does not, this term is not gonna, it's not gonna match with this term. Not all of the terms are gonna cancel out. So this term obviously is gonna equal to 0. This term cancels out, this term is going to cancel out, this term is going to cancel out. Minus the negative of the cube root of 1, which is negative 1, that is not going to cancel out. And you might have seen that the cube root of 216, which thankfully is equal to a whole number, which is 6, and then minus the cube root of 215. That's this. So these terms are what is left of our telescoping sum, essentially. So at the end, we're going to be left with 5 minus the cube root of 215 as our final answer. So once again, pretty brutal problem, but the rundown of it was that we were given lots of sequences with lots of weird cube root things. So what we wanted to do is that we wanted to get the term inside the cube root. Our ultimate goal was to represent it as the cube of a term that we knew was going to telescope because it had one positive term and we had one negative term. And ultimately, because of how the problem was contrived, how the problem was made, we were able to magically get this cube root to disappear. And then we were able to basically simplify the rest of the sum through telescoping. So once again, this is an example of a telescoping sum that doesn't really telescope in the usual way. So we still do have a lot of terms that cancel out, but it doesn't cancel out in like the fi minus fi plus 1 way, right? That you might be a little bit more used to. Okay, so the big idea, one big idea of telescoping is something called partial fraction decomposition. So partial fraction decomposition is when you're giving a fraction, right? Something like, I don't know, something like a numerator over a denominator that can be represented as the product of two different things, right? Let's say A and B. So the ultimate goal of this partial fraction decomposition for a telescoping sum is you want to create one positive term and one negative term. So in general, each of the factors of the denominator gets its own term. So we want a fraction with denominator A and a fraction with denominator B. And somehow we want to decide the two unknowns in the numerator. They don't have to be the same. So we want to, I guess, unknown 1, unknown 2. So once we subtract these, we're going to get our original fraction. So we want to choose these very carefully so that when we subtract the fractions, we get our original fraction. So you get something like AB unknown 1, B minus unknown 2, A. We want this numerator to end up being the same as this numerator. And we do that by what we essentially do is that we have to, there's a way to do this that involves basically solving for the variables of each of the values of each of these things, just like in a regular equation, like a regular system of equations. So let's take a look at an example of this, right? So let's take a look at 1 over x squared plus x minus 2. So the first thing we want to do is we want to express the denominator as the product of two things, right? Two things. And in this case, it's obvious we can factor the denominator, this polynomial over here, as x plus 2 times x minus 1. So in this case, we want to represent it as a over x plus 2 for some constant a, plus b over x minus 1 for some constant b. So what we ultimately have is that 1ax minus 1 plus bx plus 2. You want this to be, this polynomial right here, you want it to be equal to the numerator of this. You want it to be equal to 1. So you might be able to see that it turns out that if we let a equals 1 and b equals -1, then 1 over x plus 2 plus -1 over x minus 1. When we add these two terms up, we're going to get our original fraction that we started with, which is 1 over x squared plus x minus 2. So that's essentially what partial fraction decomposition is, right? So oftentimes, if we have a sum, then we're going to have a lot of these -1 over x minus 1 terms. A lot of these terms are going to cancel out with the 1 over x plus 2 terms, just because of the way that we've written the summand that we're working with. So this was an example from the handout, right? 32a over 16a to the power of 4 plus 24a to the power of 2 plus 25. Ultimately, we were supposed to see that the denominator, it was able to simplify to let's say simplify. It was able to simplify to 4a squared plus 4a plus 5 times 4a squared minus 4a plus 5. So from there, to do a partial fraction decomposition of this summand, what we did was put some unknown on top of 4a plus 5, and then plus another unknown, which is 4a squared minus 4a plus 5. So ultimately, it worked out, and then by the way we chose these two unknowns, the way we added the fractions, once we did the fraction addition method, right, we ended up with the fraction that we started with. So essentially, how I like to think of it is process of adding fractions together. You probably heard this many times before. Instead of adding two fractions together to form a sum, we're working backwards. So we're starting with the sum. The problem gives you the sum, and you have to choose the best two fractions that add up to that sum. So your goal is to choose these two fractions in a way that causes the summation to telescope. You want to cause the summation to cancel. You want to force cancellation. So anyways, onto infinite telescoping, which is telescoping with infinite many terms, right? So if f gets arbitrarily small, right? If the function f gets arbitrarily small, then this sum over here, it's ultimately going to be, all the terms are going to cancel out except for the first term, which is f of k. So all other terms are going to cancel out. But be aware that this technique only works if x is decreasing, right? If f gets arbitrarily small. The infinite sum only converges if f gets arbitrarily small. If f does not get arbitrarily small, then partial sums of the infinite sum, they're not going to approach a constant. It's going to diverge. It's not going to converge, and it's actually going to be undefined. It's going to be an undefined sum. So if you're not sure whether f gets arbitrarily small or not, just think about partial sums, because that's a little bit easier. Just think of partial sums and just use the rule that we taught you, right? Do the partial sums of this infinite series, do they approach a certain term? And if they do, then that real number is what our sum is going to evaluate to. So anyways, okay, let's take a look at this example. So 1 over 5 plus 1 plus 2 over 5 to the power of 2 plus 1 plus 4 over 5 to the power of 4 plus 1 plus 8 to the power over 5 to the power of 8 plus 1, and so on and so on and so on and so forth. And you want to evaluate this infinite sum. So the nth term in the sum in general is going to be 2 to the power of n minus 1 over 5 to the power of 2 to the power of n minus 1 plus 1, okay? So how do we make the sum telescope? So the first thing you might try is to factor one of these terms. And it turns out that if you try to factor one of these terms directly, it's not going to work. And because this isn't like difference of squares or something, or like, I don't know, like factorials or something like that. It's not like that. So where do you go from here? Because we can't factor this denominator very easily. So we can't really use partial fraction decomposition yet. We have to be a little bit more clever. So I mentioned earlier difference of squares, right? So the key thing is to pick up on the fact that this seems almost like difference of squares, except the negative ones are turned into positive ones. So what if we can write our term as the difference of two terms with denominators that are difference of squares, right? So what this means is that we're looking for, there's a little bit of wishful thinking, right? So we're looking for a way to represent this summand as the sum of some difference of squares minus some difference of squares. All right. So where do you go from here? So the reason why I brought difference of squares in the first place is because of the well-known factorization, right? So 5 to the power n minus 1 plus 1 times this. The product of these two terms is going to end up being 5 to the power of n minus 1. So there's something interesting. So this is motivated by the fact that exponents, right? They're increasing powers of 2. So this is what suggests the difference of squares approach. So, okay, so where do you go from here? So let's say we have, so let's use some visual thinking. So we're going to start with one denominator of the form something like this, and the next denominator is going to look something like this. Okay, and okay, so where are we going to go from here? So okay, so what we want to do here is gonna so what we're gonna do is gonna look at we want to create, what we want to do is we want to create 2 to the power of n minus 1 in the numerator, right? So hold on, I have to check something. So yeah, okay. So we want to create, what we want to do is we want to create a power of 2 in the numerator. So let's say we have a here and we have b here. So what we want to do is, wait, sorry. Sorry, I wrote the terms wrong. So anyways, what we want to do here is to essentially, those are terms, do some cancellation. So what we want to do here is to essentially create a term, right? So let's say b here, a here. We want to write this as 5 to the power of 2n plus 1 minus 1, and then a times 5 to the power of 2n minus 1 plus 1. Sorry. Minus b. And our ultimate goal is to be able to write this as 2n minus 1 over 5 to the power of 2n plus 1. We want to write this term as 2 to the power of n minus 1. No. Sorry, I keep getting that wrong. Okay. So, okay, let me shoot. So once again, we're starting with the term. Sorry, I'm being a bit vague because my app is glitching a little bit. Okay. So I want to write it something like this. So what we want to do is that we want to choose our A and B in such a way that when we add our fractions together, we're going to end up with something that looks a little bit like this. And something like this, okay? So we want one of our terms to be equal to 5 times 2n minus 1. Wait, no, 5n times 2 minus 1. So, sorry, something like this, okay? So what we're going to guess is that this comes from the A term. This comes from this term. So using some wishful thinking, we're going to put 2n over here, okay? So this becomes something like something like this. So now, how do we get this plus become minus? So the key to this problem is to realize that to do that, we just let b equal 2 to the power of n plus 1. So now, all of our problems have gone away. And so then our problems are gone away because this is going to be a fraction of n, and this is going to be a fraction of n plus 1. Our index has shifted essentially. So so once again, we're gonna simplify this to 1 over 4. So this is going to be 1 over 4 minus 1 over minus 2 over 24, right? 25 minus 1 plus 2 over 24 minus 4 over 124 and so on, right? So ultimately, all of these terms are going to cancel, and our final answer is 1 over 4. So once again, sorry about that because my tablet was glitching for a second. So anyways, our next problem is going to be factorials. We're going to talk a little bit about factorials. So a lot of telescoping problems, they're going to involve factorials in some way. So this is going to be problems like this, right? So the key to working with factorial problems is to always be aware of the recursive definition of factorials, because each factorial, you can write it as a certain number times the previous factorial. So So the key to realizing this is that n plus 1 factorial equals n plus 1 times n factorial, and sometimes you'll need it's also equal to n squared plus n times n minus 1 factorial, something like this. You'll be using stuff like this. So always keep track. So you're always going to be thinking about indexes. You're going to be thinking about how do we create the f minus f of I? How do we create the f of I plus 1, right? So let's take a look at this problem. Once again, an infinite summation. So the first thing that should strike you is that our denominator is not the product of two terms. It's the sum of two terms. And that's always bad because you should always be trying to factor denominator, or if you can't factor denominator, then you should find some kind of alternate way like we did in the last one. So anyways, let's take a look at this one, right? So let's take a look at the general form of a summand in this case. So the key to realizing this is that you write n plus 1 factorial as n factorial plus n plus 1 times n plus 1, right? So now you can factor the denominator. Now I can factor it like something like this, okay? This becomes n plus 2 factorial with n plus 1 at the top, okay? So now we've represented our denominator in a much better way, because instead of being the sum of two terms that we don't really know how to work with, it's now the product of a bunch of terms. We just have a factorial in the denominator. So now the key here is to rewrite this term as n plus 2 over n plus 2 factorial, and then minus 1 over n plus 2 factorial, okay? And we're summing this from when n equals 0 to infinity. So this is our new sum. This is our new sum. And now this becomes n over 1 over n plus 1 factorial. So now finally we've created our f of I, which is 1 over I plus 1 factorial, and we've created our f of I plus 1, which is 1 over n plus 2 factorial. So once again, most of these terms are going to cancel, except for the very first term, which is just going to be 1 over 0 plus 1 factorial, which is just equal to 1. So that is the answer to this factorial question. So once again, the key is to always think about factoring, always think about multiplication in the denominator. So you should think of addition in the numerator, because the numerator is when we're going to be splitting the sum into 2. But in the denominator, you should always be thinking about multiplication, because that's how you're going to be working with these partial fractions, right? You're going to be splitting one fraction into two fractions, and then these two fractions add up to the fraction that we were given. So that's all about multiplication. Okay, our last topic, which is going to be splitting into multiple parts. So we've talked about like the most basic type of telescoping, which is going to be f of I minus f of I plus 1. You write each summand like that. We've talked about stuff like f of I minus f of I plus 2, something like that, stuff like that. And this stuff, in these types of problems, there's going to be a little bit more terms that are left over. So most of the terms are going to cancel, but some more of them will be left over. You should always, once again, you should always be keeping track of the terms that are left over after you've canceled a lot of the terms in your sum. Anyways, we're given this problem. And we're asked to sum which is a really bad one, isn't it? Just has to sum this from this quantity from n equals 1 to infinity. So how are we going to go about this? So usually there are two factors in the denominator, right? There's going to be two factors in the denominator. So that's where you get your two fractions. But in this case, there's three factors in the denominator. So that's a little bit tough. So how are we going to be dealing with this? So actually, the way you're supposed to do this is to just first think about splitting the two parts. Just think about splitting the two parts. So in this case, we're going to try to do some partial fractions with one denominator is n plus 1 squared, and one denominator is 1 over n squared. Something like this. So in this case, what is a and what is b? So this comes out to a times n plus b n squared plus 2n plus 1 over the denominator, right? Okay. So now you have to start thinking about how are we gonna be able to create this numerator from these two, a and this b. So first of all, obviously b has to be equal to -1 in order to create this term. Okay. So first we all have a -1 over n. So now what is going to be what is a going to be? So ultimately, I'll leave it to you to verify, but a it's ultimately going to be it's going to come out to n. It's going to come out to n plus. It's going to come out to n plus 3. It's going to come out up to n plus 3. So that's that. So once you add these two fractions, the numerator of the fraction is gonna magically become n minus 1. That's what I'm saying. So now what do we go from here? So because this is still very, very far from a telescoping sum. So now So now we have a -1 over n, right? So what if we're able to create a positive 1 over n plus 1? Wouldn't that be great? Because then we can create a lot of telescoping, right? And it turns out we can do exactly just that. We can do something like, we can represent n plus 3 over n plus 1 squared. We can represent this as 1 over n plus 1 plus 2 over n plus 1 squared, okay? So we can represent this term in this way, okay? So now, we have, so now let's okay. So I'm not gonna get to this anyways. What we're gonna get to is that we're gonna rewrite our sum. We're gonna rewrite our sum as the following. So we're gonna have 2n plus 1 squared. This is the term that we still don't really know how to deal with. We're gonna have the 1 over n plus 1, and we're gonna have the -1 over n. Okay? So now this becomes something like this. 2n plus 1 squared plus this. So basically we've split our sum. We've split our summand, our very large summand with three components. We've split it into two sums. So the first sum we still know how to deal with. The second sum, it's going to be pretty easy because our second sum it's just going to be a telescoping sum. So it's going to be negative 1/2 minus 1 plus 1/3 minus 1/2 plus 1/4 minus 1/3. These terms will cancel. These terms will cancel. These terms. So all that's left is going to be -1. I'll leave that to you to verify. And how do we deal with this term over here, right? So it turns out that this sum, you can only evaluate it with something known as the evaluation problem, which is just the sum of the reciprocals of all all positive squares, right? 1/1 squared plus 1/2 squared plus 1/3 squared. So you'll learn later that this sum is going to be equal to pi squared over 6. It's going to miraculously be equal to pi squared over 6. But anyways, hopefully one day you'll know how this is proven. We cannot cover it in this course. It's far too advanced. But anyways, once we know this, we can see that this sum actually becomes pi squared over 3 minus 2. Because don't forget that we are missing this term over here. So we have the -2. So our final answer is going to be pi squared over 3 minus 3. So that's going to be our final answer for this problem. So it might seem like a little bit like cheating, right? Because we had to use this thing over here. So usually contests will just give this fact to you, because I do see it quite often in contest problems. So what they'll do is that they'll give you this fact that the sum of the reciprocals of all the perfect squares is equal to pi squared over 6. And then you'll have to use that fact to determine a particular problem, essentially. So you'll be using this fact to solve a particular summation problem. And usually once you were given this problem, you should be thinking about, how do I get the sum of the reciprocals of the squares in here? How do I get the pi squared over 6 in here? So in this case, what we did was split our sum, our big sum, into a telescoping sum and a sum that involves the formula for the sum of the reciprocals of the perfect squares. Yeah, so anyways, I was going to cover like a monstrously difficult purple comet problem, but it would take me like 15 minutes. So I'm just going to end the class on time, on schedule. So on to the conclusion. So what did we do? What did we do today? So today we looked at the technique of splitting a summand in our sum into 2 or more smaller pieces. So splitting the summand. So we looked at how this can be used to split one sum, a complicated sum, into 2 smaller sums that are a little bit easier to deal with. We're going to look at how we split like, and we learn how to force cancellation through a technique called telescoping sums. Telescoping sums. This is very important. Don't forget it. The next thing that we did was we looked at we looked at infinite series that can be solved through using telescoping sums, and this can only be used if partial sums of this infinite sum approach a particular value, or if like our function f of I approaches 0, let's say it approaches 0, or some other number, usually 0. But anyways, infinite sums like that. Infinite sums. So the last thing we learned was how to split into multiple pieces. We looked at an example where we're splitting into 3 pieces, and sometimes you'll have to split into 4 or 5 or 6, but we just decided not to show those types of problems to you in this lecture. But anyways, next week, please do the homework. It should be posted either today night or tomorrow. Work week 3. Please do the writing problem because it is helpful for your proofwriting ability, and we enjoy just reading all of your solutions. So don't forget the writing problem. Okay. The next thing you should keep in mind is to rewatch the lecture if you had anything you had trouble understanding. I know that some parts I was a little bit vague, but you can rewatch the lecture if you feel like that would help you. Maybe a better option would just to reach me directly. You can reach me directly on Discord if you want like a particular concept explained, a particular problem explained. I could probably explain it a little bit better now if it's just you and me, right? So you can reach me directly on Discord, and I can answer any individual concepts you had, and I can respond directly to any of your concerns. The next, and just keep practicing. Don't let the earlier theory, like don't forget about the earlier theory. It's probably just as important, if not more important than this. And I think that's it for this lecture. If you have any questions, then you can ask me now. If otherwise, I'm gonna stop the recording here.